Hi, my name is Ryan O'Hara, and I'm here to talk to you today about how I recently worked with a partner to develop a lightweighted and cooled jacket for a turbine engine. Specifically, I have worked, did a webinar with a joint webinar with Velo 3D and KW Micropower. So KW Micropower is a small startup turbine engine manufacturer, specifically turbine engine generator manufacturers. The idea is that they wanted to take this part and optimize it for additive manufacturing. And in doing so, to do that, we basically, they wanted to realize some benefits to their design. Specifically, they came to us and they said, hey, using nTop, can we lightweight this part and then add cooling to it? And in doing so, can we improve the overall heating and efficiency of the engine? And sure enough, we said yes, we could. And so I'll kind of skip ahead and not give you the full presentation here, but the idea is that we wanted to take this part and we wanted to simply variably shell this part such that we could put a cooling jacket around this part and effectively lower the weight of the part. So for an aerospace application, if it was going to be a flying generator, and then we wanted to add the cooling so that in this scenario, they would actually use fluid, in this case, the fuel, to preheat the fuel. And by preheating the fuel, they're going to get advanced combustion efficiency. And in addition to that, they're going to keep their generator cooler, so they're going to give an even higher efficiency. And I'm going to kind of quickly go over how we implemented that. And I'll introduce this concept of variable shelling. And the idea is that, and this is one of our core functionalities, is that we can take a part and we can shell it. In traditional CAD tools, this is a very difficult operation and often fails. Right? In our software, not only does it not fail, we actually give you an incredible amount of control over how to do that. And then fundamentally, when you're able to do this, we're actually able to bring this cooling volume into the object, in this case, run some simulation upon that part. And we're able to do that both in Discovery Live and in ANSYS Fluent. And then fundamentally, additionally, we're going to talk a little bit more about this area, but we can actually simulate the thermal results associated with both and compute both displacement, temperature, and stress associated with the part. So let's get into how we go over the variable shelling part, and we'll save the thermal sim and other pieces for another time. So the idea here is that I would just simply import an object. In this case, it's the housing here. And this housing, as you can see, is just a solid part right now, right? Nothing fancy going on here, just a big solid part that was traditionally machined before out of a big block of aluminum. And so what we have to do is we have to take this CAD representation and we have to actually bring it in as an implicit body. And if you've seen our technology before, basically we're going to wrap a math equation around this object, okay? And that's going to allow us to do some things here. And one of those things that we can do is we can actually do this constant shell operation. So if I open this block up, this is it's called variable shell, but in here I have a value called, it's just 2.5 millimeters. And so what I'm going to do is I'm going to show that part isolated here. And you can see in this scenario, I've actually just added a 2.5 shell operation to this part, and this extends over the entire part. Okay. So, although this is variable, you'll notice that in here we have a little icon that looks like a field or a droplet of water, and that ripple is going out. Well, that field, we can actually put some advanced things in there. And what I'm actually going to do is, or what I've set up, is that I'm actually placing planes at the top, bottom, and mid plane of this object. And if I turn on my section view, now you can see that there's these three planes, and we're going to use these planes to help control some of the features of this part. So these pieces are here. What I'm actually going to do is I'm going to generate a field. You'll notice that there's a field around this mid plane. I'll turn some parts off here. And if I turn on my field generator, and 500, you'll notice that as I turn on these values, or let's actually go back to the distance field, you'll notice I have a positive region up here above the plane and a negative region below. Well, I actually want to shell this part, and what I wanted to do is I want to shell this part so that it's actually thicker in the middle and thinner at the top and bottom, right? And so I'm going to do that. I'm actually going to perform an absolute operation here, where I'm actually going to now, by taking the absolute value, I have away from this plane, I'm going to be 0 to increasing values, and I'm going to be 0 decreasing values below it. And now I can actually take that field and put it into a ramp function. And a ramp function is just a transfer function in this case to actually translate distance away from this plane into the shelling variability that I would like. And so if you notice, if I probe these values now, if I start at this midplane, I'm going to have a value of minus 2.5 millimeters, which is one of my inputs here. And then it's going to basically increase until I reach a distance 113 millimeters away, and where it's beginning to become a constant 5 value. And you can see that those values are in here, and they're related to this ramp function. So all I'm doing is converting a distance away from a plane into the amount of distance that I want to shell a body. And then when I'm able to basically pass this field into this part, you can see, I'm gonna have to section cut this part now, that I'm basically able to, you'll notice that the further away I am from the object down here, the thicker it gets, which corresponds to my value of 5 millimeters offset. So down here at the bottom, it's 5 millimeters, right? And here at the mid plane, it's going to be 2.5. And here at the top, it's back to 5 millimeters again. Pretty cool. So this, and then I can readily change these values on the fly. Maybe I don't want it to be, maybe I want it to be minus 10 millimeters. Well, you know, all I have to do is ask, and then nTop is going to compute that for me. In this case, this isn't necessarily a great value, but it is quite easy to do, and I can easily just change the middle piece there. But we're going to go back to minus 5 here. So, you know, in this scenario, we actually wanted, in partnership with KW Micro, they actually wanted to be thicker at the ends and thinner in the middle, because they're actually going to apply bolting attachments here at the top and the bottom, and then we're going to have higher stress. And so just like a butted tube, they wanted it thick at the top and bottom and thin in the middle. Okay. You know, one other scenario that we wanted is that they're going to be mounting this generator here in the middle, and so we actually wanted to make this internal piece also thicker as well. And if you'll notice, this is actually hollow in the interior, and although maybe good for cooling, it's not necessarily good for a structural application. And so what we're going to do is we're going to take the same concept associated with the plane, but now I'm going to actually include an axial field. And I am including an axial field by using an axis variable. And again, you'll notice that there's a field associated with this object. So if we slide this guy up, right, and maybe turn on some contours, and go here, you'll notice that we have a circular field that's emanating from this object. And if I probe these values, it's basically 0 to a distance away. And so now if I turn on a ramp function, I've done the same thing here, where basically at the center of this object, I am having 7.5 millimeters. And then I actually specified that I want a distance away from this object to, I said 50 millimeters away, that I'm basically going to keep, I basically just want to keep this solid section nice and thick out to a certain distance, and then I'm going to start decreasing those values. And if I turn on the original CAD body, you'll notice that this corresponds with this inner ring. So I want a nice solid piece here at this radius, right? And then I want it to get thinner as I extend out. And so I've set up my ramp function to do that as it is. So let's show you what that radial shell looks like by using that field. And again, I'm just passing the original housing implicit and the axial field in now. Show that, isolate it, and turn off the field viewer, and we'll cross-section this. And so now you'll notice our part is actually solid here in the middle. And if I were to actually turn on that the top to bottom shell, I basically have two different values here. So in this scenario, it's nice and thick here in the middle, thin on the outside. But now in this orange, that's my original plane to shell. So now I can actually get the combination of those two by simply unioning those two objects together. And now you'll notice I have this purple value. So I have solid in the middle, thick at top and the bottom, and overall this is going to meet our objectives of this interior volume. And that's quite easily done. Yep. So that's all I really wanted to show you today, just how quick and easy you can do a scenario like this and basically cut out 40 to 50% of your mass, and then and capture that in your design. If you wanted to, you can leverage our simulation blocks here and perform thermal and structural analysis to determine the effects of the shelling and make sure it still complies with your part. But overall, thanks for your time today, and look forward to working with you all in the future. Take care. Bye.